All right, back with another example. This time we're working 419 on page 92, which has to do with sliding a box across a surface, taking friction into account. So I've got the basics here to save a little bit of time. Got my free body diagram with the four forces involved. I've also listed my coefficient of friction, which basically is it's a ratio. It's the ratio of the friction force to the normal force. All right, and if you, this will be important later, but if you rearrange that, then you get friction is equal to the coefficient times the normal force. So, as always, we'll go through our steps. First step in the guesswork is to write our free body diagram. Second step is to write our force summations. So I'm going to start off with the in the horizontal, because that's where the acceleration would happen in this case, which is what we're ultimately trying to find here. Remembering that Newton's second law says that a net force causes a mass to accelerate, in this case in the x direction, in the horizontal. And then we list what forces are responsible for that net force. So in the horizontal direction, we've got two forces involved. One of them is the horizontal component of the applied force. Since the force is being applied at an angle, we only want to consider the horizontal component when we're summing, when we're adding the horizontal forces. All right, in this case, since that's the adjacent side to the angle, that would be cosine. In the opposite direction, we have friction. And if I expand that a little bit, or rewrite that, the mass and the acceleration of the system of the box is going to be due to the horizontal component of the applied force and the friction force, which, recall, is that. So there's my summation in the x direction, in the horizontal. In the vertical, again, Newton's second law says net force is responsible for making a mass accelerate. In this case, though, since the box is on a surface, it is neither accelerating up nor down, so the net force is zero in the vertical. However, there are two forces that are responsible for this. One of them, I'm sorry, I take that back, three forces. All right, one of them is the normal force acting upward. Another one is going to be this vertical component of the applied force, because it's basically going to have the effect, if you will, of lightening the load from that normal force. It's going to be pulling up as well. So we're going to, since that's pulling in the same direction, we're going to go ahead and add that, and it's on the opposite side of the angle, so that'd be, we're going to use sine, and then in the opposite direction is the weight of that box. So where we go next would be, let's see, we need to know before we can do anything here in the horizontal, notice how we need the normal force. So that's where the y, where the vertical direction is going to come into play, because we need to figure out this normal force so before we can do anything else. So I'm going to go ahead and, noticing that we have, so here's our equation. All of this adds up to a net force of 0. So I'm going to rearrange to solve for the normal force. So if I do that, I get the weight of the box minus that vertical component of the applied force. Now what I can do is I can take this and I can substitute this in for the normal force, because this is really what we want. Ultimately, we want to solve this. So if I do that, I end up with, in the horizontal, because that's where the acceleration is occurring, the horizontal component of the applied force minus coefficient of friction times, and this is going to be times the normal force, which I'm going to substitute in this. Then it's just a matter of solving for the acceleration. So rewrite all this. Okay, just dividing mass out from both sides. So then this would be my final expression, and from here it's just a matter of plugging in the numbers, chugging out the answer. Now, yes, you could have, if you would prefer, you could find the weight of the object separately. You could find, you can go back here and find the components of these separately and use those numerical values. But sometimes I just prefer to go ahead and solve it algebraically and then plug everything in. Hope this helps. Ask me in class if you have any questions.